In the heart of the Pacific Northwest, rumblings deep below the surface, recent swarms of earthquakes, slight ground shifts, faint whispers of volcanic gas have scientists on edge. The Cascade volcanoes, once silent, are showing the same subtle signs that preceded catastrophes like the 1980 Mount St. Helens eruption and the 1700 megathrust quake. If the deadly Cascade volcanoes really are waking up, is North America facing the next mega eruption? And what can history teach us before the ground shakes again? About 7,700 years ago, a mountain in southern Oregon ripped itself apart. Mount Mazama, once towering over the landscape, erupted in a series of explosions so violent that the summit collapsed inward, leaving behind the deep blue basin now known as Crater Lake. That eruption released nearly 50 cubic kilometers of ash and pumice, enough to blanket over 1 million square kilometers of western North America. In places near the vent, ash deposits stacked up meters thick. Even 1,000 kilometers away, a faint gray layer settled on the ground. The eruption column soared as high as 50 kilometers into the stratosphere, scattering ash as far as Alberta and the Great Plains. For weeks, the sun dimmed and the air thickened, as forests and lakes across the Pacific Northwest were smothered by falling debris. But Your subscription is the single best and totally free way to support the channel. It tells YouTube that you value these stories, and it directly helps me continue to find and share them with you. If you'd like to see more, please consider hitting that subscribe button. Thank you so much for watching. Massive ashfall is only one side of Cascade Volcano's destructive power. About 5,600 years ago, the northeast flank of Mount Rainier suddenly gave way. In minutes, a massive wall of mud, rock, and water, what geologists call a lay-hiar, roared down the White River Valley. This Osceola mud flow carried 2.3 cubic kilometers of debris, enough to bury entire towns, and traveled over 110 kilometers, reaching what is now the Puget Sound lowlands. Near the mountain, the deposits piled up to 20 meters thick, while even in the Seattle area, several meters of ancient mud still lie hidden beneath modern neighborhoods. The flow's velocity, tens of kilometers per hour, left little time for anything in its path to escape. Today, cities like Ording, Sumner, and Kent sit atop these remnants, a silent testament to the reach of volcanic mud flows. Volcanologists, piecing together these histories from layers of ash and mud, map the extent of ancient disasters to understand what might happen again. Tracing the Mazama ash across the continent and the Osceola deposits through buried river valleys, they reveal how Cascade volcanoes threaten both with sudden explosions and with relentless valley-filling floods. The difference is more than academic. Ashfall can choke skies and snarl air traffic thousands of kilometers away, while lahars can devastate communities in less than an hour. Both hazards, written in the land and in the memories of those who study it, define the scale of risk that modern monitoring and emergency plans must confront. On the evening of January 26, 1700, an immense earthquake struck the Pacific Northwest. The ground heaved and coastal forests dropped by more than 1 meter, flooding with saltwater almost instantly. Along tidal rivers from Northern California to Vancouver Island, entire stands of western red cedar died together, their roots drowned in brackish mud. Today, their gray trunks, ghost forests, still stand at the water's edge, silent witnesses to a night when the land itself changed shape. The exact timing of this event comes not from local memory, but from across the Pacific. That same night, waves crashed ashore in villages along the Japanese coast. There had been no earthquake in Japan, only a sudden, powerful tsunami that battered fishing boats and flooded rice fields. Japanese officials carefully recorded the event, puzzled by the absence of any local shaking. Centuries later, seismologists matched these orphan tsunami records to the Cascadia coastline, calculating the 10-hour journey across the ocean and pinpointing the earthquake's moment, about 9 o'clock in the evening Pacific time, January 26, 1700. In the Pacific Northwest, the evidence is buried in the earth. Paleoseismologists dig trenches through tidal marshes to reveal a sharp boundary, dark peaty soil overlain by a sudden layer of marine sand and mud. Radiocarbon dating and stratigraphic analysis show that this shift happened all at once. Marshes sinking as much as 2 meters in a matter of minutes. Sand sheets carried inland by the tsunami capped the subsided marshes, marking the reach of the waves. These deposits, found at dozens of sites, all date to the same winter, matching the tree ring kill date of the ghost forests and the Japanese tsunami logs. By combining these independent lines of evidence, written records from across the ocean, the silent testimony of drowned trees, and the geological signature of sudden subsidence, scientists have reconstructed the precise timing and scale of the 1700 Cascadia megathrust earthquake. With an estimated magnitude between 8.7 and 9.2, the rupture tore along more than 1,000 kilometers of the subduction zone, releasing centuries of built-up strain in a single devastating event. This is the benchmark for seismic hazard in the Pacific Northwest. Not a story from legend, but a date fixed in the calendar, written in both human and natural archives. In July 2025, Mount Rainier's summit region was rattled by a swarm of 1,172 earthquakes, the largest cluster recorded there in over a decade. Pacific Northwest Seismic Network scientists, using a dense web of 20 seismic stations, captured each jolt and tremor in high resolution. Most of these quakes struck at depths between 1.2 and 3.7 miles beneath the summit, with the strongest registering a magnitude 2.42 on July 11th. The swarm's intensity was most pronounced in its opening hours, when event rates climbed to as many as 40 per hour, far above the usual background of a handful per month. Seismologists relied on template-matching algorithms to sift through the data, identifying hundreds of small, sharp-onset events that would have gone unnoticed just a few years ago. These volcano-tectonic earthquakes, with frequency peaks between 2 and 12 Hz, are signatures of brittle rock fracturing under stress. Manual review and automated cataloging confirmed that the vast majority of events were shallow and tightly clustered, radiating laterally rather than stacking upward. By July 21st, over 780 events had been manually checked, with additional microquakes flagged for further analysis. The temporal pattern of the swarm revealed a classic diffusion profile. The initial burst on July 8th quickly tapered, but a secondary cluster flared up on July 24th and 25th before gradually returning to background levels by the end of the month. This pattern, along with the lateral spread of hypocenters, fit well with models of fluid migration rather than magma ascent. Unlike magmatic swarms, where one might expect to see a train of upward migrating events or sustained volcanic tremor, the Rainier sequence lacked low-frequency or hybrid signals. Instead, the swarm was dominated by high-frequency, abrupt-onset quakes, each lasting only a few seconds. Depth cross-sections and migration maps from the PNSN catalog showed the densest clouds of epicenters directly beneath the summit, with scattered events extending outward along known fracture zones. The maximum depth of activity, just under 4 miles, is typical for hydrothermal-driven swarms in the Cascades. At no point did the seismic network detect the kind of harmonic tremor or long-period events that would suggest magma was forcing its way upward. The scale of the July 2025 swarm stands out in the historical record. Rainier typically experiences 1 or 2 swarms per year, but the sheer number and density of this episode, over 1,000 events in less than a month, provided an unprecedented dataset for cross-sensor checks and waveform analysis. These numbers now serve as a new baseline for future monitoring, allowing scientists to calibrate their detection systems and refine their models of volcanic unrest. For the researchers at PNSN and the USGS Cascades Volcano Observatory, every quake in this swarm added another data point to the evolving story of Rainier's restless summit baseline. While seismometers light up during earthquake swarms, scientists rely on a broader toolkit to separate volcanic unrest from background noise. At Mount Rainier, the July 2025 swarm triggered a coordinated review of ground deformation and gas emissions, 2 lines of evidence that, together with seismicity, help reveal whether magma is on the move beneath the surface. Satellite-based radar, especially Sentinel-1 interferograms, provided a detailed record of ground motion across Rainier's summit and flanks. By stacking dozens of passes from June through August, geodesists searched for any sign of uplift, subsidence, or lateral spreading that might indicate magma intrusion. The results were consistent and clear. No deformation stood out from baseline seasonal or weather-related variation. GPS stations, part of the UNAVCO network, confirmed this stability. Their continuous time series showed no significant vertical or horizontal shifts, no bulging, no creeping, no warning signals like those seen at Mount St. Helens before the 1980 eruption. The mountain's surface remained steady, even as hundreds of small earthquakes rattled deep below. Attention then turned to volcanic gas, a sensitive tracer of subsurface processes. On August 4, 2025, USGS gas specialists and National Park Service staff conducted an airborne survey over Rainier's prominent fumaroles. Instruments measured carbon dioxide, sulfur dioxide, and hydrogen sulfide emissions, comparing real-time readings to years of archived data. The numbers told a reassuring story. Emission rates and gas compositions matched previous surveys, with no spikes in magmatic gases or shifts in chemical ratios. Continuous ground-based sensors at established vents echoed the airborne findings, showing only minor fluctuations within the normal range for a glacier-clad volcano with a robust hydrothermal system. These results were not unique to Rainier. Across the Cascade Arc, similar checks at Mount Baker, Hood, and the Three Sisters produced much the same picture. Sentinel-1 stacks and GPS logs showed no ground inflation or deflation at any of these peaks during periods of heightened seismicity. Gas monitoring at Baker, which has a history of vigorous fumarole activity, likewise revealed no anomalous emissions. Even at Three Sisters, where subtle uplift in early 2024 drew attention, a multi-instrument review led USGS teams to maintain the existing alert level. The absence of coherent deformation or magmatic gas signals was decisive. For USGS gas specialists and geodesists, these converging lines of evidence are vital. Seismic swarms alone can be ambiguous, sometimes linked to fluid migration, sometimes to magma ascent. But when ground motion and gas data remain flat, the case for a magmatic cause weakens. The July 2025 Rainier swarm, for all its size and intensity, left no fingerprint in the surface or the air. Instead, the data converged on a hydrothermal explanation. Hot water and steam, not rising magma, drove the unrest. This multi-sensor approach, seismometers, satellites, and gas detectors working in concert, now defines Cascade volcano monitoring. It is the convergence, not any single signal, that guides both scientific interpretation and public safety decisions. Mount Rainier, Mount St. Helens, and Mount Hood stand at the top of the USGS National Volcanic Threat Assessment, each ranked as very high threat in the 2018 report. These volcanoes are not only active, but sit close to major cities, placing hundreds of thousands of people and critical infrastructure within reach of their hazards. Rainier in particular is singled out for its lahar risk to communities in the Puyallup and White River valleys, while St. Helens and Hood are noted for their explosive potential and proximity to downwind populations. Reassuringly low. Despite the drama of recent earthquake swarms, the numbers behind eruption risk remain reassuringly low. For the July 2025 Rainier swarm, over 1,100 earthquakes in less than a month, the probability of a transition to eruption was officially assessed at well under 2%. USGS and Pacific Northwest Seismic Network analysts, drawing on decades of monitoring and pattern recognition, point out that these swarms are a regular feature of Cascade volcanoes. Most are driven by shifts in hot water and gas deep underground, not by rising magma. The annual chance of a major eruption at any single Cascade volcano remains below 0.2%, and during non-magmatic swarms, short-term probabilities do not increase. Not predictions. The National Volcanic Threat Assessment organizes volcanoes into categories based on a blend of eruption history, recent unrest, and the number of people and assets at risk. St. Helens ranks second nationwide, Rainier third, Hood sixth, and Three Sisters seventh. Mount Baker, Shasta Crater Lake, and Lassen also make the high threat list, though their recent activity has been quieter. These rankings are not predictions. They are tools for guiding monitoring resources, emergency planning, and public awareness. Modern science. Analysts at the Cascades Volcano Observatory and partner networks continuously update threat profiles as new data come in. Their approach is rooted in statistics, not speculation. When a swarm like the July 2025 Rainier event lights up the sensors, teams check for patterns. Are the quakes getting shallower? Is the ground shifting or gas composition changing? Only when multiple lines of evidence point to magma on the move do probabilities rise. Until then, the numbers remain on the side of caution, reflecting not just the power of the volcanoes, but the rigor of modern science. The threat is real, but the odds of an imminent eruption, even during the most active swarms, are much lower than most might expect. Your subscription is the single best and totally free way to support the channel. It tells YouTube that you value these stories, and it directly helps me continue to find and share them with you. If you'd like to see more, please consider hitting that subscribe button. Thank you so much for watching.